Time dilation, a fascinating aspect of Einstein's theory of relativity, occurs when an object approaches the speed of light, causing time to pass more slowly for it compared to an observer at rest. This phenomenon can be quite mind-boggling, as it challenges our everyday perceptions of time. For instance, imagine a spaceship traveling at a significant fraction of the speed of light, while astronauts aboard experience time normally. Meanwhile, observers back on Earth would notice that time for those astronauts is moving slower, creating a sort of cosmic time difference. This effect becomes more pronounced the closer the spaceship gets to light speed, leading to scenarios where astronauts could return from a journey and find that years or even decades have passed on Earth while only a short time has elapsed for them. One intriguing aspect of time dilation is its connection to gravitational fields. According to general relativity, time runs slower in stronger gravitational fields. So, if a spaceship were to travel near a massive object, like a black hole, astronauts would experience time at a different rate than those far away from the black hole's influence. This means that if you were to orbit a black hole, you could potentially experience time much more slowly compared to someone on Earth. Such scenarios open up exciting possibilities for future space travel. But they also raise questions about aging and the human experience in the vastness of space. When considering the practical implications of time dilation, one must think about the technology needed for high-speed space travel. Current spacecraft, like the Voyager probes, travel at speeds that are a tiny fraction of the speed of light, which means that time dilation effects. However, scientists are exploring advanced propulsion systems, such as antimatter engines or solar sails, which could one day allow us to approach relativistic speeds. If we can reach, say, 10 of the speed of light, time dilation would still be present, but its effects would be subtle, making it a fascinating topic for theoretical exploration rather than immediate application. The twin paradox is a famous thought experiment used to illustrate time dilation. In this scenario, one twin travels on a high-speed journey into space while the other twin remains on Earth. Upon the traveling twins' return, they find that they are younger than their sibling due to the effects of time. This paradox is not just a hypothetical situation. It has real-world implications in technologies such as GPS satellites, which must account for both special and general relativity to provide accurate positioning data. The satellite's time dilation, a fascinating concept in the realm of physics, refers to the difference in the elapsed time as measured by two observers due to relative velocity or the influence of gravity. In simpler terms, it means that time can pass at different rates for people, depending on how fast they are moving or how close they are to a massive object like a planet or a star. This phenomenon arises from Einstein's theory of relativity, which reshaped our understanding of space and time. In the context of special relativity, Time dilation occurs when an object moves close to the speed of light. For example, if a spaceship travels at a significant fraction of the speed of light, the time experienced by the astronauts on board will be less than that experienced by people back on Earth. This has been confirmed through various experiments, including those involving highly precise atomic clocks flown on airplanes, which have shown that time moves slightly slower for the clocks in motion compared to those that remain stationary. On the other hand, in the context of general relativity, time dilation is affected by gravity. The stronger the gravitational field, the slower time moves. This means that someone standing on the surface of a massive body like Earth will experience time slightly more slowly than someone far away from any massive object, like an observer in deep space. This has practical implications, especially in the realm of satellite technology. The Global Positioning System, or GPS, must account for these differences in time, or the positioning data would quickly become inaccurate. In essence, time dilation challenges our intuitive understanding of how time works, revealing that it is not a constant universal measure, but rather a flexible concept that is influenced by speed and gravity. This leads to intriguing questions about the nature of reality, as it suggests that two observers can have entirely different experiences of time, even while witnessing the same event. This idea, while difficult to grasp, highlights the complexity of the universe and our place within it, and continues to be a rich area of exploration in both theoretical and experimental physics, opening doors to deeper insights into the fundamental structure of our reality. The theory of relativity, a groundbreaking framework in physics, was first proposed by Albert Einstein in the early 20th century, specifically in 1905, when he introduced his special theory of relativity. This theory fundamentally changed our understanding of space and time, and it introduced the idea that the laws of physics are the same for all observers, regardless of their relative motion. One of the most intriguing aspects of this theory is the concept of time dilation, which states that time can pass at different rates depending on how fast an object is moving relative to another object. For example, if you were to travel in a spaceship at a significant fraction of the speed of light, you would experience time more slowly compared to someone who remained on Earth. This means that if you took a journey through space at high speeds, you could return to find that more time has passed on Earth than for you in the spaceship, which is a mind-bending realization that challenges our everyday experiences of time. Einstein's work was revolutionary, and it laid the groundwork for modern physics, influencing not just theoretical studies, but also practical applications, such as the technology behind GPS satellites, which must account for relativistic effects to provide accurate positioning data. Einstein expanded on this concept further in 1915 with his general theory of relativity, which describes gravity as the curvature of space-time caused by mass. This theory also includes the implications of time dilation in the context of strong gravitational fields, demonstrating that time runs slower in stronger gravitational fields compared to weaker ones. Einstein's theories have been confirmed through numerous experiments and observations, such as the famous observation of light bending around the sun during a solar eclipse in 1919, which served as a significant validation of his predictions. The implications of relativity have permeated various fields, including cosmology, astrophysics, and even philosophy, leading to a deeper understanding of the universe and our place within it. Special relativity, a theory proposed by Albert Einstein in 1905, fundamentally changed our understanding of space, time, and how they interact with one another. One of the most fascinating aspects of special relativity is the phenomenon known as time dilation. Time passes at different rates for observers who are in different frames of reference, particularly those moving relative to one another. To illustrate this, imagine two twins, one of whom embarks on a journey through space at a speed close to the speed of light, while the other remains. When the traveling twin returns home, they will find that they have aged significantly less than their sibling, who stayed behind. This is not just a theoretical idea. It's a consequence of how time is perceived differently depending on relative motion. The core principle of time dilation arises from the fact that the speed of light is constant for all observers, regardless of their relative motion. This means that if one observer is moving at a high velocity, their measurement of time will differ from that of a stationary observer. As an object approaches the speed of light, time for that object slows down relative to an observer who remains at rest. This effect, while it may seem counterintuitive, has been confirmed through numerous experiments. For instance, highly accurate atomic clocks flown on airplanes or placed on satellites have been shown to tick more slowly compared to clocks on the ground, demonstrating that time is not an absolute constant, but is affected by speed and gravity. Moreover, time dilation is not just limited to speeds near the speed of light. It also occurs in the presence of strong gravitational fields, as predicted by Einstein's later work in general relativity. For example, clocks on the surface of the Earth run slightly slower than those on satellites orbiting above, due to the weaker gravitational pull experienced by the satellites. This means that GPS satellites must account for both special and general relativity to provide accurate positioning data, as their onboard clocks run faster than those on Earth due to time dilation effects. In practical applications, the implications of time dilation are profound. It affects everything from space travel considerations, where astronauts must account for the time they spend moving at high speeds, to the functioning of modern technology like the Global Positioning System, which relies on precise time measurements. The phenomenon of time dilation not only challenges our intuitive understanding of time, but also invites us to explore deeper questions about the nature of reality itself, revealing a universe that behaves in ways that are often surprising. In the realm of special relativity, time dilation is a fascinating concept, and it describes how time can pass at different rates for observers who are in different frames of reference, especially when they are moving relative to one another. The primary equation used to calculate time dilation is derived from the Lorentz transformation, which is central to Einstein's theory of special relativity. The formula for time dilation can be expressed as 2 of light in a vacuum, which is approximately 299,792 kilometers per second, or about 186,282 miles per second. This equation reveals that as the relative velocity v approaches the speed of light c, the denominator approaches 0, which means that tan becomes significantly larger than time, for the moving observer is moving more slowly compared to the stationary observer. Are created when cosmic rays collide with atoms in Earth's atmosphere. Muons have a short half-life, and if they were not subject to time dilation, they would decay before reaching the surface of the Earth. But because they are moving close to the speed of light, they experience time more slowly, allowing many of them to reach the surface. Another important aspect of time dilation occurs in the context of gravitational fields, where time can also be affected by gravity, a concept explored in general relativity. However, in special relativity, we focus specifically on the effects. The implications of time dilation stretch beyond theoretical discussions. They have practical applications, particularly in the technology of GPS satellites. These satellites are in orbit around the Earth, moving at high speeds compared to observers on the ground. If the effects of time dilation were not accounted for, the GPS system would quickly become inaccurate, leading to significant navigational errors. Additionally, physicist Albert Einstein introduced the concept of simultaneity, which is closely related to time dilation. According to special relativity, two events that are simultaneous in one frame of reference may not be simultaneous in another frame of reference moving relative to the first. This leads to the conclusion that time is not an absolute quantity, as it can change the speed of light, which is approximately 300,000 kilometers per second, plays a crucial role in the concept of time dilation, a phenomenon predicted by Albert Einstein's theory of relativity. According to this theory, as an object moves closer to the speed of light, time for that object begins to slow down relative to a stationary observer. This means that if you were to travel in a spacecraft at speeds approaching the speed of light, your experience of time would differ significantly from that of someone who remained on Earth. For instance, if a spaceship could somehow travel at 99% of the speed of light, time aboard the ship would pass much more slowly compared to time on Earth. This has been confirmed through various experiments, including those involving atomic clocks placed on fast-moving jets or satellites, where the clocks on the fast-moving vehicles recorded less time than those that remained stationary on the ground. The implications of time dilation are not just theoretical. They have practical applications in technologies such as GPS, where the satellites orbiting the Earth are moving at speeds that require adjustments for time dilation effects, ensuring that the systems provide accurate location data. Additionally, the concept ties into the idea that light, being the fastest thing in the universe, serves as a cosmic speed limit, which affects how we perceive time and space. As objects accelerate towards this limit, the fabric of space-time itself is warped, leading to fascinating consequences, such as the possibility of experiencing time differently depending on your velocity. When we think about black holes, for instance, the extreme gravitational fields they create also lead to significant time dilation effects, where time can slow down dramatically near the event horizon compared to a distant observer. This interplay between speed, light, and time reveals a profound truth about our universe. It suggests that time is not a constant, as we often perceive in our daily lives, but rather a dynamic aspect of the universe that is influenced by speed and gravity. The relationship between speed and the passage of time challenges our intuitive understanding, showing us that the universe operates under principles that can be quite counterintuitive, yet deeply fascinating. And as we continue to explore the cosmos, we uncover even more layers of complexity in these fundamental concepts. Time dilation is a fascinating concept in the realm of physics, particularly in the context of Einstein's theory of relativity, and it highlights how time is not a fixed entity, but rather a variable that can change based on speed and gravity. When comparing objects moving at different velocities, time dilation manifests in unique ways. According to the theory of special relativity, as an object approaches the speed of light, time for that object slows down relative to an observer who is at rest. This means, for instance, if you were to travel in a spaceship at a significant fraction of the speed of light, time would pass more slowly for you compared to someone remaining on Earth. This effect becomes more pronounced the closer you get to the speed of light, which is approximately 299,792 kilometers per second, or about 186,282 miles per second. To understand this better, consider two twins. When the traveling twin returns, they would find that less time has passed for them than for the twin who stayed on Earth. This is often referred to as the twin paradox, and it illustrates time dilation beautifully. The key factor here is the relative velocity between the two objects. The faster the traveling twin moves, the more pronounced the effect of time dilation becomes. On the other hand, for objects moving at much lower velocities, like cars or airplanes, the effects of time dilation are negligible and almost imperceptible. For example, if you were to fly in an airplane, the difference in time experienced compared to someone on the ground is so small that it is not noticeable. However, this does not mean it doesn't occur. It simply indicates that at everyday speeds, the effects are too Interestingly, gravitational time dilation also comes into play when we consider objects in strong gravitational fields. According to general relativity, time passes more slowly in stronger gravitational fields. So, if you were near a massive object, like a black hole, time would move more slowly for you compared to someone far away from such a gravitational influence. This adds another layer of complexity to how we understand time dilation, as it means that both velocity and gravity can alter the way time flows. So, when comparing objects moving at different velocities, the crucial takeaway is that the closer an object gets to the speed of light, the more time slows down for it relative to a stationary observer. This results in fascinating scenarios. The twin paradox is a fascinating thought experiment in the realm of physics, particularly in the study of relativity, and it beautifully illustrates the concept of time dilation, a phenomenon predicted by Albert Einstein's theory of special. Imagine, if you will, a scenario where one twin, let's call her Alice, embarks on a journey through space, traveling at a speed close to the speed of light, while her twin brother, Bob, remains on Earth. According to the principles of special relativity, time is not absolute. Instead, it can vary depending on how fast an object is moving. So, while Alice is zooming through the cosmos, time for her slows down significantly compared. When Alice eventually returns home, she discovers that she has aged only a few years, while Bob has aged many more, perhaps even decades. This counterintuitive situation arises because, from Alice's perspective, she experiences relativistic effects due to her high-speed travel, while Bob experiences the regular flow of. This situation, however, can lead to confusion, hence the term paradox, as both twins could argue that the other is the one who has experienced time differently, creating a puzzling scenario. Yet, the resolution lies in the fact that Alice's journey involved acceleration and deceleration, which breaks the symmetry between the two twins. Bob, remaining in an inertial frame, experiences a consistent passage of time, while Alice's frame changes during her journey. The twin paradox not only highlights the strange and wonderful nature of time, but also serves as a practical illustration of time dilation, as it reveals how motion at significant speeds can result in measurable differences in aging, thus showing that time is indeed relative, differently based on one's velocity through space. Gravitational time dilation and time dilation due to high speeds are both fascinating aspects of Einstein's theory of relativity, yet they stem from distinct mechanisms. Gravitational time dilation occurs in the presence of a gravitational field where time runs differently depending on the strength of that field. For instance, the closer you are to a massive object like a planet or a star, the slower time passes for you compared to someone who is farther away. This phenomenon has been confirmed through experiments. such as those involving atomic clocks, placed at different elevations. Clocks situated at higher altitudes, where the gravitational pull is slightly weaker, have been observed to tick faster than those at lower altitudes, demonstrating how gravity can influence the flow of time. On the other hand, time dilation due to high speeds, often referred to as relativistic time dilation, occurs when an object moves at a significant fraction of the speed of light. According to Einstein's special theory of relativity, as an object approaches the speed of light, time for that object slows down relative to an observer who is at rest. This means that if you were traveling in a spacecraft at near light speeds, you would age more slowly compared to someone remaining on Earth. This effect has been illustrated in various thought experiments, including the famous twin paradox, where one twin travels in a high-speed rocket while the other stays on Earth, leading to a situation where the traveling twin returns younger than their counterpart. The key difference between these two types of time dilation lies in their causes. Gravitational time dilation is a result of the influence of mass and gravity, while relativistic time dilation is due to the effects of speed and motion. Both effects have profound implications for our understanding of the universe, particularly in fields such as astrophysics, where they play crucial roles in the behavior of objects near massive bodies, like black holes, and in the study of high-velocity particles in accelerators. Understanding these concepts not only deepens our insight into the nature of time itself, but also highlights the intricate relationship between space, time, and gravity, revealing the complexities of our universe that continue to captivate scientists and enthusiasts. The Lorentz factor, often denoted by the Greek letter gamma, plays a crucial role in the realm of physics, especially when it comes to understanding the effects of time dilation, a phenomenon that arises from the theory of relativity proposed by Albert Einstein. This factor, which is mathematically expressed as gamma equals 1 divided by the square root of 1 minus the square of the velocity of an object divided by the square of the speed of light, highlights how time and space interact in ways that differ significantly from our everyday experiences. As an object moves closer to the speed of light, the Lorentz factor increases, which leads to a greater effect on time as perceived by observers in different frames of reference. For instance, if a spaceship were to travel at a significant fraction of the speed of light, the astronauts aboard would age more slowly compared to people on Earth, a result that can be attributed to this factor. This means that if a twin were to travel in that spaceship and then return, they would find that less time has passed for them than for their twin who stayed on Earth, a scenario often referred to as the twin paradox. Moreover, the significance of the Lorentz factor extends beyond just time dilation. It also affects measurements of length and mass, leading to what is known as Lorentz contraction and relativistic mass increase. As an object approaches the speed of light, not only does time slow down for it relative to an outside observer, but the object itself also appears to contract in length from the perspective of the observer. demonstrating the interconnectedness of time and space. This understanding reflects a profound shift in our conception of reality. It challenges the notion of absolute time and space, suggesting instead that both are relative and depend on the observer's velocity. This idea has been confirmed through numerous experiments, such as observations of particles moving at high speeds in accelerators, where the predicted time dilation effects occur exactly as the Lorentz factor suggests. Thus, the Lorentz factor is not merely a mathematical concept. It serves as a bridge to understanding the fundamental nature of the universe, illustrating how our perception of time is intricately linked to the speed at which we travel through space. This insight has profound implications for modern physics, influencing everything from the way we understand cosmic events to the technologies we develop, such as GPS satellites, which must account for these relativistic effects to provide accurate positioning data. In essence, the Lorentz factor helps us navigate the complex and often counterintuitive in the realm of physics, particularly in the theory of relativity proposed by Albert Einstein. Time is not an absolute concept, but rather it is perceived differently depending on the observer's state of motion, especially when comparing observers in different inertial frames. An inertial frame is essentially a perspective from which an observer is either at rest or moving at a constant velocity. And according to Einstein's special relativity, time can actually pass at different rates for observers who are in different inertial frames. This phenomenon is known as time dilation, and it becomes particularly significant when objects are moving at speeds close to the speed of light. To illustrate this, imagine two observers. One is on a fast-moving spaceship, traveling at a significant fraction of the speed of light, while the other is on Earth, standing still relative to the spaceship. For the observer on the spaceship, time appears to pass normally, but when they look back at the Earth, they would notice that the clock on Earth is ticking slower than their own clock. Conversely, the observer on Earth would perceive the spaceship's clock as ticking more slowly. This effect arises from the fundamental principles of relativity, which state that the laws of physics are the same for all observers, and as such, the measurements of time are affected by relative motion. The mathematical framework behind this concept is rooted in the Lorentz transformations, which describe how measurements of time and space change for observers in different inertial frames. According to these transformations, time intervals measured by two observers will differ if they are moving relative to one another. As the relative speed between the observers increases, the difference in time perception becomes more pronounced. This is not just a theoretical idea. It has been confirmed through various experiments, such as those involving atomic clocks placed on fast-moving jets or satellites, which have been shown to measure less elapsed time compared to identical clocks on the ground. Moreover, this time dilation effect is not just limited to high-speed travel. It also applies in the presence of strong gravitational fields, as described by Einstein's general theory of relativity. For instance, time runs slightly slower on the surface of a massive body, like the Earth, compared to time experienced by an observer far away from such gravitational influences. This means that an observer at sea level on Earth will experience time a bit differently than someone at a high altitude, where gravity is weaker. The implications of these effects stretch beyond mere academic interest. They have practical applications. Global Positioning System, GPs, satellites, time dilation, a fascinating consequence of Einstein's theory of relativity, suggests that time moves differently for observers in different frames of reference, particularly when those frames are moving at significant velocities, gravitational fields. One of the most compelling pieces of experimental evidence supporting this concept comes from the observation of atomic clocks. In one famous experiment, scientists used precise atomic clocks flown around the world on commercial aircraft. When these clocks were compared to stationary clocks on the ground, the airborne clocks showed a slight time difference, indicating they had experienced less time due to their high speed, confirming the predictions of special relativity. Another significant experiment involved muons, which are subatomic particles that decay relatively quickly. When muons are produced in the upper atmosphere by cosmic rays, they travel toward the Earth at nearly the speed of light. According to classical physics, these muons should decay before reaching the surface. But due to time dilation, they experience time more slowly than stationary observers on Earth. As a result, many more muons reach the surface than we would expect without considering relativistic effects, providing strong experimental evidence for time dilation. In addition to these, scientists have also conducted experiments using satellites equipped with atomic clocks, such as the Global Positioning System, or GPS. The GPS satellites orbiting Earth experience both gravitational time dilation due to their altitude in a weaker gravitational field and velocity time dilation because they are moving quickly relative to observers on the ground. Engineers must account for these differences to ensure the accuracy of GPS measurements, which is another practical demonstration of time dilation in our everyday lives. Furthermore, the Haffel-Keating experiment, where atomic clocks were flown around the world on commercial flights in the 1970s, also confirmed time dilation. The results showed that the clocks on the planes were behind the clocks that remained on the ground, aligning perfectly with the predictions made by relativity. This experiment, along with others, has created a robust body of evidence demonstrating that time dilation is not just a theoretical idea, but a real, measurable phenomenon that affects our understanding of the universe and the nature of time itself. As we probe deeper into the implications of time dilation, it becomes clear that this concept challenges our intuitive understanding of time and space, revealing a universe that is far more complex and interconnected than we might have previously imagined. Each of these experiments adds a piece to the puzzle, confirming that time is indeed relative, and that our experience of it can vary dramatically depending on our time dilation, a fascinating phenomenon predicted by Einstein's theory of relativity has significant implications for astronauts traveling at high speeds, particularly those venturing into space at velocities approaching the speed of light. Essentially, time dilation occurs because time is not a constant. Instead, it can be affected by relative motion and the influence of gravity. When astronauts travel at high speeds, such as during missions that reach a significant fraction of the speed of light, their experience of time differs markedly from that of people on Earth. This difference arises because, according to the theory of relativity, time moves slower for objects in motion compared to those that are stationary. For instance, if an astronaut were to travel on a spacecraft moving at 90 the speed of light, they would experience time passing more slowly than someone remaining on Earth. While they might age only a few years during their journey, many more years could pass on Earth. This means that if an astronaut were to embark on a long space mission at such high speeds, they could return to find that decades have elapsed back home, while they have only aged a few years. This effect, although it sounds like science fiction, has been supported by experimental evidence, such as the observations made with atomic clocks on fast, moving jets and satellites, which have shown measurable differences in the passage of time compared to clocks on Earth. The implications of time dilation are profound, especially when considering future space travel and the potential for interstellar journeys. If humanity were to explore distant star systems traveling at substantial fractions of the speed of light, the aging process of astronauts would be dramatically affected due to this relativistic effect. Therefore, while astronauts experience less aging during their travels, the loved ones they leave behind would age significantly, creating emotional and social complexities for those involved. Moreover, scientists are continually investigating the effects of time dilation in various contexts, not just with astronauts, but also in understanding the universe's fundamental laws. The concept of time dilation raises intriguing questions about the nature of time itself and how it can be relative depending on one's frame of reference. As technology advances, the potential for human travel across vast distances in space becomes more plausible, and understanding time dilation will be crucial for planning future missions, ensuring the health and well-being of astronauts, and preparing for the societal impacts of such voyages. This fascinating interplay between physics and human experience not only enriches our understanding of the universe, but also highlights the complexities of space travel and the profound ideas that stem from time dilation. A fascinating concept from Einstein's theory of relativity. Applications that impact our everyday lives, particularly in modern technology such as GPS systems. When we think about GPS, we usually just consider it a tool for navigation, but in reality it relies on the precise timing of signals sent from satellites orbiting the Earth. These satellites are moving at high speeds, and they are also farther from the Earth's gravitational field compared to someone standing on the surface. This difference in speed and gravity means that the clocks on the satellites actually run at a different rate than clocks on Earth. To put it simply, the satellites experience what is known as special relativity, which tells us that time moves slower for objects in motion, and general relativity, which tells us that time moves faster in weaker gravitational fields. The result is that the clocks on the satellites tick slightly faster than those on Earth by about 38 microseconds each day. If engineers did not take this time difference into account, GP's calculations would quickly become inaccurate, leading to navigational errors that could accumulate to several kilometers each day, making it impossible to rely on GPS for precise positioning. Additionally, time synchronization is vital in various technologies beyond GPS. For example, in telecommunications, data is transmitted between different locations that require precise timing to ensure that signals arrive in the correct order. Time dilation effects are taken into account in the design of systems like fiber optic networks, where timing discrepancies could cause significant data loss or corruption. The synchronization of clocks across the globe relies on a network of atomic clocks, which are incredibly accurate. But they must also account for time dilation effects due to differences in altitude and relative motion. Another interesting application of time dilation can be found in particle physics. Scientists working at particle accelerators like Kern's Large Hadron Collider deal with particles moving at speeds close to the speed of light. These particles, such as muons, also experience time dilation, which allows them to exist longer than they would if they were at rest. Researchers study these effects to understand fundamental aspects of physics, including the behavior of matter and the forces of the universe. In summary, while time dilation may seem like a theoretical concept, it has very real and practical implications in our modern technological world, affecting everything from global positioning systems to telecommunications and advanced scientific research, showing just how interconnected our understanding of time and space really is. Time dilation, a fascinating aspect of Einstein's theory of relativity, plays an essential role in how we understand time, especially in the context of space travel and the synchronization of clocks, both on Earth and in space. To put it simply, time dilation occurs when an object moves at a significant fraction of the speed of light, or when it is situated in a strong gravitational field, which causes time to pass at different rates. This means that a clock on a spacecraft moving at a high speed will tick more slowly compared to a clock on Earth, where gravitational effects and speed are relatively minor. For instance, astronauts aboard the International Space Station, which orbits Earth at about 17,500 miles per hour, experience a slight form of time dilation. This means that when they spend time in space, less time passes for them compared to people on the ground. Over the course of a long mission, this difference can accumulate to a measurable extent, resulting in astronauts aging just a tiny bit less than their peers back on Earth. In practical terms, this has implications for how we synchronize systems that rely on precise timing, such as GPS satellites. GPS satellites are in a higher gravitational field and also move at high speeds compared to clocks on Earth. Engineers must account for both gravitational time dilation and the effects of their velocity to ensure that If they didn't make these adjustments, the GPS system would quickly become inaccurate, leading to errors in navigation that could be significant, especially for military and aviation purposes. Moreover, the synchronization of clocks is crucial, not just for navigation, but also for communication systems, scientific experiments, and more. Clocks on satellites are set to tick faster than those on Earth to compensate for the effects of time dilation experience. This means that when the satellites transmit signals back to Earth, those signals are adjusted to reflect the difference in time passage, ensuring that the data received is accurate. Interestingly, this phenomenon is not just a theoretical concept. It has real, world applications, and is a vital consideration for technology that relies on precise timing. For example, in particle physics experiments, such as those conducted at the Large Hadron Collider, scientists have to consider time dilation when measuring the behavior of particles moving at speeds close to light. These particles experience time differently than stationary observers, influencing the outcomes of experiments and our understanding of fundamental physics. In conclusion, time dilation is a crucial factor that affects how we synchronize clocks on Earth and in the realm of physics, especially when discussing the fabric of space and time. Einstein's theory of relativity introduces some fascinating concepts, one of which is that occurs as a result of the relationship between velocity and time. According to Einstein's equations, particularly in his theory of special relativity, time is not a constant universal measure, as we might commonly assume, but rather it is affected by how fast an object is moving through space. This means that the faster an object travels, the more pronounced the effects of time dilation become. To illustrate this, consider a scenario where a spaceship travels at a significant fraction of the speed of light, which is about 300,000 kilometers per second. As the spaceship accelerates towards this incredible speed, time aboard the ship begins to pass more slowly compared to time on Earth. This effect can be quantified by the Lorentz factor, which is a mathematical expression that describes how much time, length, and relativistic mass increase as an object approaches the speed of light. The Lorentz factor is derived from the equation as the velocity VA gets closer to This leads to the idea of twin paradox, where if one twin travels in a high-speed spaceship while the other remains on Earth, the travelling twin would age more slowly compared to the twin who stayed behind. When they reunite, the twin who journeyed through space would have experienced less time than the twin who remained on Earth. This is not just a theoretical exercise. It has practical implications, such as in the operation of the Global Positioning System, or GPS, satellites. These satellites orbit the Earth at high speeds and experience less gravitational pull than objects on the ground, which results in both velocity, space-time dilation, and gravitational time dilation. The combination of these factors means that the clocks on these satellites tick slightly faster than those on Earth, necessitating adjustments to ensure accurate positioning data. Furthermore, time dilation affects our understanding of the universe at large, particularly when observing distant galaxies, or cosmic acceleration plays a crucial role in the phenomenon of time dilation. Particularly in the context of space travel, a concept grounded in Einstein's theory of relativity. According to this theory, time does not pass at the same rate for everyone, and this is particularly noticeable when dealing with high speeds or significant gravitational forces. When a spacecraft accelerates, it changes its velocity relative to an observer, which in turn affects how time is experienced on board the ship compared to someone who remains stationary, say back on Earth. As the spacecraft accelerates, it approaches a significant fraction of the speed of light, which is about 299,792 kilometers per second. At these high speeds, time on the spacecraft will appear to pass more slowly compared to time on Earth. This effect is known as time dilation, and it means that for astronauts traveling at these high velocities, less time would pass for them than for those who remain on Earth. For example, if a spaceship were to travel at 90s of the speed of light for what feels like a year to the crew, several years could pass on Earth, making the journey seem quite paradoxical. What's fascinating is that acceleration itself can also contribute to time dilation. When a spacecraft accelerates, the passengers inside can feel a force pushing them back into their seats, similar to the feeling you get in a car when accelerating quickly. This acceleration can create a scenario where time is experienced differently, not just due to speed, but also because of the change in velocity. As per Einstein's equivalence principle, which states that being in an accelerating frame can be indistinguishable from being in a gravitational field, this means that acceleration effectively stretches time for those on board. Moreover, the effects of acceleration and the resulting time dilation can become more pronounced in scenarios involving extreme acceleration, such as in a rocket launch. The intense forces experienced during such rapid changes in speed can lead to significant differences in time perception. This aspect of relativity has been confirmed through various experiments, including those involving atomic clocks flown on fast, moving aircraft, which have indeed shown that time passes differently depending on the speed and acceleration of the clock's frame of reference. As a result, When we consider the implications for long-distance space travel, the understanding of time dilation becomes critical. For interstellar missions, where spacecraft might travel at speeds approaching that of light, the crew's experience of time would be dramatically different from that of people on Earth. This leads to intriguing possibilities. Time dilation, a fascinating concept derived from Einstein's theory of relativity, challenges our everyday understanding of time in profound ways, stretching our imagination and compelling us to rethink our experiences. In the realm of everyday life, we perceive time as a constant, ticking away at the same rate, regardless of our circumstances. However, when we delve into the realms of high speeds, such as those approaching the speed of light, or in the presence of strong gravitational fields, time behaves unexpectedly. For instance, if you were to travel in a spacecraft at a significant fraction of the speed of light, you would experience time more slowly compared to someone remaining on Earth, meaning that while you age just a little during your journey, years could pass for those waiting back home. This effect is not merely theoretical. It has been confirmed through experiments, such as those involving atomic clocks flown on jets, which have shown measurable differences in elapsed time compared to clocks on the ground. Moreover, gravitational time dilation adds another layer to this intriguing phenomenon. In areas of strong gravity, like near a black hole, time moves slower than in regions of weaker gravity. Imagine an astronaut orbiting a massive planet, experiencing time at a different rate than someone on the planet's surface. This means, theoretically, if you were to spend time near a black hole, you could return to find that many more years have passed for those who remained far away from such a powerful gravitational influence. These ideas fundamentally alter our perception of time, transforming it from a simple linear progression that we can easily fathom into a complex interplay of space, speed, and gravity. The implications are staggering, suggesting that our everyday understanding of past, present, and future might not hold true in extreme conditions. This leads us to consider philosophical questions about the nature of time itself, such as whether the past truly exists, or if it is merely a construct of our memories, influenced by our position in space and the forces acting upon us. In essence, as we explore the universe and its mysteries, time dilation reminds us that time is not as absolute as we once thought, and it invites us to ponder the very fabric of reality, with each new discovery revealing just how intricate and interconnected. To understand how scientists measure time dilation in particles moving close to the speed of light, we first need to grasp the concept of time dilation itself, which is a fascinating prediction of Einstein's theory of relativity, stating that time passes at different rates for observers in different frames of reference, particularly when one is moving at speeds approaching the speed of light. Scientists often use high-energy particle accelerators, which are massive machines that accelerate particles to speeds very close to the speed of light, allowing researchers to observe the effects of time dilation firsthand. For example, in experiments involving particles such as muons, which are created when cosmic rays collide with particles in Earth's atmosphere, scientists can measure how long these particles exist before decay. When muons are at rest, they have a very short lifespan, about 2.2 microseconds. But when they are moving close to the speed of light, their observed lifespan increases significantly due to time dilation. This means that while a stationary observer on Earth would measure the muon to decay after just 2.2 microseconds, an observer moving with the muon would measure a much longer lifespan, as the fast-moving muon experiences time more slowly compared. By studying the number of muons that reach the surface of Earth before they decay, scientists can calculate how much time dilation occurs, using the relation between the speed of the muon and the effects predicted by Einstein's equations. Furthermore, scientists might also utilize particle colliders like the Large Hadron Collider, where protons are accelerated to near-light speeds, allowing for precise measurements of time dilation effects. Here, the particles are often detected by their decay products, and researchers can analyze how long the particles exist before decaying, comparing this with their predicted decay times based on their velocities. This comparison provides empirical evidence supporting the theory of relativity, reinforcing our understanding of how time behaves under extreme conditions. Additionally, precise timing technology, including atomic clocks, plays a crucial role in these experiments. These clocks are incredibly accurate and can measure tiny differences in time, allowing scientists to detect the minute effects of time dilation in particles. When particles are moving very fast, the clocks on board the particle might tick at a different rate compared to those on Earth, providing another way to observe and measure the effects of time dilation. Through these methods, scientists have consistently confirmed the predictions of relativity, demonstrating that time dilation is not just a theoretical concept, but a measurable phenomenon that has real time dilation, a fascinating consequence of Einstein's theory of relativity, has implications for space missions to distant planets, particularly as we consider journeys that may take years or even decades in the quest to explore our solar system and beyond. Essentially, time dilation refers to the difference in the elapsed time as measured by two observers, due to a relative difference in velocity or gravitational fields. In simpler terms, time moves slower for objects that are traveling at speeds close to the speed of light, compared to those that are at rest or moving at slower speeds. When planning missions to distant planets, such as Mars or even further out to the outer planets like Jupiter and Saturn, we must consider how time dilation could affect both the astronauts on board a spacecraft and those back on Earth. For instance, if a spacecraft were to travel at a significant fraction of the speed of light, the crew on board would experience time passing more slowly than people on Earth. This means that while the astronauts might age only a few years during their journey, many more years could pass back home. This effect raises intriguing questions about the psychological and social aspects of space travel. How would astronauts cope with the knowledge that while they are exploring new worlds, their friends and family may age significantly during their absence? It could also affect mission planning and communication between the crew and mission control, as the timing of messages could be impacted, complicating coordination and support. Furthermore, the implications of time dilation extend to the scientific experiments conducted during these missions. For example, consider the impact on biological experiments, where understanding aging, growth and development in microgravity could be influenced by the differing rates of time experienced by the crew. Knowing that time is not a constant, and that it can stretch or contract based on speed, could inform how we conduct research in space and interpret the results. In addition to these psychological and scientific considerations, time dilation also has practical implications for navigation and mission design. The calculations for trajectories, fuel usage, and the timing of maneuvers would need to account for the relativistic effects of time. As spacecraft travel faster, engineers must incorporate these factors into their designs and mission plans, ensuring that they can respond to changes in time perception while maintaining a safe and efficient journey. Moreover, as we look to the future, with concepts like interstellar travel becoming a topic of discussion, the implications of time dilation become even more pronounced. Proposals for spacecraft that could reach nearby stars could involve speeds where time dilation becomes a significant time dilation. A fascinating consequence of Einstein's theory of relativity becomes particularly significant when we consider communication between spacecraft traveling at close to that of light. As these spacecraft accelerate to relativistic speeds, the effects of time dilation mean that time passes differently for those aboard compared to observers back on Earth or on other spacecraft that are not moving nearly as fast. For astronauts aboard a fast-moving spacecraft, time would pass more slowly relative to those on Earth. So while they might experience only a few hours of travel, years could pass for those monitoring their journey from a distant planet or from mission control on Earth. This discrepancy could create substantial challenges for effective communication, as messages sent from a spacecraft might take longer to arrive than anticipated, making coordination with mission control increasingly complex. For instance, if a spacecraft is traveling at 90s of the speed of light, the time taken for a signal to reach Earth would be affected by the time dilation experienced by the astronauts. While the spacecraft crew might send a transmission every hour of their time due to the relativistic effects, those signals would arrive on Earth spread out over a longer period, and the people on Earth would perceive the events as happening at a much slower rate than the crew themselves are experiencing. This means that if a spacecraft needs to react to a situation rapidly, the time lag in communication could lead to critical delays in decision, making processes, creating potential safety risks. Moreover, the Doppler effect, Another relativistic phenomenon would also play a role in communication. As the spacecraft moves towards or away from the source of communication, the frequency of the signals would be altered, which could distort the messages being transmitted. If the spacecraft is approaching a communication satellite, the signals would be compressed, leading to a higher frequency, while if it is moving away, the signals would be stretched, resulting in a lower frequency. This would not only make it difficult to interpret the received messages, but could also create misunderstandings regarding the urgency or nature of the information being conveyed. To mitigate these issues, spacecraft might need to utilize advanced technology, such as quantum communication, which could theoretically allow for instantaneous information transfer, irrespective of the relative motion between the spacecraft and Earth. However, as of now, such technologies are still in the experimental stages and are far from being a practical solution for spacecraft operating in relativistic conditions. In summary, the implications of time dilation for communication between spacecraft traveling at relativistic speeds are profound, bringing challenges that require innovative solutions to time dilation. A fascinating concept from Einstein's theory of relativity suggests that different rates, depending on the relative speed of an observer, as well as the strength of gravitational fields they experience. For human space travel to distant star systems, the effects of time dilation could have profound consequences. When a spacecraft approaches the speed of light, which, while currently beyond our technological capabilities, is a theoretical consideration for future interstellar travel, time aboard the spacecraft would pass more slowly compared to time on Earth. This means that astronauts could experience only a few years of travel time, while many more years, or even decades, could pass back home. This discrepancy raises significant implications, such as the emotional and psychological challenges faced by astronauts who might return to find that their families have aged significantly, or that they have missed major societal changes on Earth. Additionally, the technology required to achieve such high speeds would need to be incredibly advanced, potentially involving the manipulation of space-time itself, like theoretical concepts such as warp drives or wormholes. Moreover, the physical effects of prolonged exposure to such conditions could also present challenges. For instance, the human body is accustomed to Earth's gravity and time frame, and prolonged exposure to different gravitational fields and time perception could lead to There's also the question of communication. If astronauts are traveling at relativistic speeds, sending messages back to Earth would take longer than expected, complicating the relationship between the traveling crew and those remaining on Earth. Furthermore, if we consider missions that might last several years, the isolation of space travel, combined with the effects of time dilation, could create a unique set of psychological stresses for the crew, affecting teamwork and mental well-being. Another aspect to consider is the technological and logistical challenges of planning such missions. With the knowledge that time dilation could lead to significant differences in aging and life experiences, mission planners would have to account for these factors, possibly even preparing for a situation where the crew could return to a vastly changed world. The concept of time dilation also invites broader philosophical questions about the nature of time itself, as well as humanity's place in the universe. The idea that time is not a constant and that it can stretch and compress based on speed and gravity challenges our everyday understanding of time as a linear experience. All these factors suggest that while the idea of traveling to other star systems is thrilling, it comes with complex ramifications that require serious consideration. As we continue to explore the possibilities of interstellar travel, understanding the concept of simultaneity, which refers to whether two events occur at the same time, can change dramatically when we consider the effects of time dilation, a fascinating consequence of Einstein's theory of relativity. In classical physics, time was viewed as absolute and universal, meaning that if two observers situated in different places looked at the same event, they would agree on when it happened, regardless of their motion or position. However, once we enter the realm of relativity, things become much more complex. According to Einstein's special relativity, time is not the same for everyone, especially if they are moving relative to one another at significant fractions of the speed. When one observer is moving very fast compared to another, time will appear to pass more slowly for the moving observer from the perspective of the stationary observer. This means that if two events are simultaneous in one frame of reference, they may not be simultaneous in another. To illustrate this, consider a scenario involving two observers. Alice is standing on a platform, while Bob is traveling in a spaceship moving close to the speed of light. If they both witness two lightning strikes hitting the ends of the platform at the same time, Alice, who is stationary, will see these strikes as simultaneous. However, for Bob, who is moving towards one of the strikes and away from the other, the light from the lightning strikes will reach him at different times. The faster an object moves through space, the more pronounced the effects of time dilation become. The implications of this are profound, especially when considering scenarios involving high-speed travel or even the effects of gravity on time, as described by For instance, when thinking about GPS satellites orbiting the Earth, which travel at high speeds relative to someone on the surface, their onboard clocks actually tick a bit slower due to time dilation effects. This means that synchronization of the satellite clocks with those on Earth must take into account these relativistic effects, or else errors in positioning would occur. Moreover, in extreme cases, such as near a black hole, the differences in the passage of an observer far away from the black hole would see an object falling towards it, slow down, appearing to freeze at the event horizon, while from energy plays a crucial role in the phenomenon of time dilation, particularly for objects that are moving at significant fractions of the speed of light. According to Einstein's theory of relativity, as an object accelerates and its speed approaches the speed of light, the amount of energy required to continue accelerating it increases dramatically. This increase in energy is linked to the object's mass, which effectively becomes greater due to its velocity, a concept known as relativistic mass. As the energy of the moving object increases, time appears to pass more slowly for that object, relative to an observer who is. This means that if you were traveling in a spaceship at near light speed, while only a short time might pass for you, much more time could elapse back on Earth. This effect is not merely theoretical. It has been confirmed through various experiments, such as those involving high-speed particles in accelerators and precise measurements with atomic clocks. For instance, particles known as muons, which are produced when cosmic rays collide with particles in the Earth's atmosphere, decay more slowly when they are moving at speeds close to the speed of light compared to when they are at rest. This is a direct observation of time dilation in action, where the energy of the particles influences their decay rate and hence the passage of time as perceived in different frames of reference. Moreover, the interplay between energy and time dilation is also evident in the context of gravitational fields. According to Einstein's general relativity, gravity can influence time as well. Therefore, an object with a high gravitational energy, such as a massive star, would experience time differently than an object with lower gravitational energy, like a small planet. This means that time runs slower in stronger gravitational fields. And when you combine this effect with the influence of energy from motion, you get a fascinating tapestry of how time is not a constant, but rather a variable that is deeply intertwined with energy and motion. In practical terms, this understanding of energy and time dilation has implications for technologies such as GP's satellites, which must account for both the effects of their high speeds and the weaker gravitational field they experience compared to objects on Earth. If these relativistic effects weren't taken into account, Jeep systems would quickly become inaccurate, leading to significant errors in navigation. Thus, energy, whether from motion or gravity, plays a vital role in shaping our experience of time, demonstrating that time is not just a simple ticking clock, but a complex interplay of energy, motion, and gravity that defines when a spaceship travels. Dilation becomes a fascinating phenomenon, deeply rooted in the theories of relativity proposed by Albert Einstein. According to Einstein's theory of special relativity, time does not pass at the same rate for observers in different frames of reference, especially when one of those frames is moving at a significant fraction of the speed of light. For those aboard the spaceship, as they accelerate to 90s of the speed of light, they would experience time passing normally, just as it does for us on Earth. However, for observers on Earth, the situation would be quite different. To an external observer, such as someone standing on Earth, time aboard the spaceship would appear to move much slower. This effect is a result of the Lorentz factor, which describes how much time, length, and relativistic mass increase, or appear to increase at at 90s of the speed. Light, the Lorentz factor, is approximately 2.29, meaning that for every 1 hour that passes on the spaceship, about 2.29 hours would pass on Earth. This means that if the spaceship traveled for what felt like a short journey of 5 years, the implications of this are profound, not just for theoretical physics, but also for space travel and our understanding of the universe. If astronauts were to embark on a journey to a distant star at this speed, they would age significantly less than their friends and family back home. This difference in the flow of time can also lead to what is often referred to as the twin paradox, where one twin travels into space at relativistic speeds, while the other remains on Earth. Upon returning, the traveling twin would be younger than their Earth-bound sibling, illustrating the counterintuitive nature of time in our universe. Such scenarios, while theoretical, have been supported by experimental evidence. For instance, atomic clocks flown on jets have shown that as they move faster relative to stationary clocks on Earth, they indeed register slightly less passage of time, confirming Einstein's predictions. Moreover, the effects of time dilation are not just limited to extreme speeds. They also occur in strong gravitational fields, as predicted by general relativity. For a spaceship traveling at high speeds, the combined effects of both velocity and any gravitational fields it might encounter could further complicate the experience of time for the crew. This time dilation, a fascinating aspect of Einstein's theory of relativity, becomes particularly significant when we consider the extreme gravitational forces of black holes, which are regions in space where gravity is so intense that nothing, not even light, can escape. According to the theory, time is not a constant, unchanging entity, but rather it can be influenced by the presence of mass, particularly in the case of very massive objects like black holes. As one approaches a black hole, the gravitational pull increases dramatically, causing time to pass more slowly relative to observers who are far away from this gravitational influence. This effect, known as gravitational time dilation, means that if you were to orbit a black hole or even get closer to its event horizon, the point of no return, time for you would move at a different pace than for someone far away in space, away from such strong gravitational forces. For example, an astronaut who ventures near the event horizon of a black hole might experience only a few minutes passing, while those observing from a distance could witness years or even centuries elapsing. This creates a curious and perplexing scenario where one could theoretically age much slower than their friends or family who remain far away, leading to what some refer to as time travel, albeit in a non-traditional sense. The insights into time dilation around black holes have profound implications for our understanding of the universe. Scientists use these principles to explore the nature of space-time and the interplay between gravity and time. The concept is not merely theoretical. It has been confirmed through various experiments, such as observing the behavior of atomic clocks on Earth versus those on satellites, which indeed show that time moves slightly faster in space due to the weaker gravitational field there. Moreover, the famous thought experiment involving the twin paradox illustrates these principles well. One twin travels near a black hole, while the other remains on Earth. Upon reuniting, the travelling twin would be younger than the one who stayed behind, showcasing the reality of time dilation in extreme gravitational fields. This becomes incredibly interesting when we consider the immense energy and conditions around black holes, where space-time is warped to such a degree that the usual rules of physics. As we delve deeper into the universe, understanding how time behaves near black holes not only challenges our fundamental perceptions, but also opens up discussions about the fabric of reality itself. It raises questions about the nature of time, whether it is a linear progression or something more complex and intertwined with the geometry in the fascinating world of physics, particularly in the domain of Einstein's theory of relativity. The role of the observer in the phenomenon of time. Dilation is pivotal. And understanding this concept can be quite mind-bending. Time dilation occurs when two observers are moving relative to each other, or when one is in a different gravitational field than the other. This means that time, which we often consider to be a universal constant, is actually experienced differently depending on the observer's frame of reference. Imagine two twins, one staying on Earth and the other traveling in a spacecraft at a significant fraction of the speed of light. According to the traveling twin, time on Earth appears to be moving faster than time on the ship, while for the twin on Earth, time on the ship appears to be moving slower. This difference arises because the travelling twin is in a different inertial frame compared to the twin on Earth, experiencing time at a different rate due to their high velocity. It's not that one twin is aging more slowly or faster in an absolute sense, but rather that their experiences of time are distinct, influenced by their relative speeds and the principles outlined in Einstein's special relativity. Additionally, gravitational time dilation, which is a part of Einstein's general relativity, comes into play when considering how gravity affects the passage of time. For instance, a clock that is closer to a massive object, like a planet or a star, will tick more slowly compared to a clock that is farther away. This means that an observer near a black hole would experience time. Both of these scenarios highlight that the observer's position, speed, and the strength of the gravitational field they are in are critical in determining how they perceive the flow of time. This brings us to the role of the observer, which is not passive. Rather, it's deeply intertwined with the nature of reality itself. Observers in different locations with different velocities perceive time differently, making it a subjective experience rather than an absolute one. This subjective nature of time is a cornerstone of modern physics, challenging our intuitive understanding of time as something that ticks uniformly for everyone. The implications of this are profound, suggesting that our understanding of the universe is not only shaped by the physical laws, but also by the perspectives of those who observe it. When scientists conduct experiments, such as using precise atomic clocks on airplanes or satellites, they can measure these differences in time dilation and confirm Einstein's predictions in the realm of physics, particularly when discussing the theories of relativity, the concept of frames of relativity, the concept of frames. Reference plays a crucial role in understanding how time and distance are perceived. To put it simply, a frame of reference is essentially a perspective from which measurements are made, and this can significantly influence how we perceive time and space. When we talk about time, we often think of it as a constant, flowing at the same rate for everyone. But according to Albert Einstein's theory of relativity, this isn't the case. Instead, time can appear to move differently, depending on the speed at which an observer is traveling, as well as the strength of gravitational fields they are experiencing. For instance, if you were to travel close to the speed of light, which is about 299,792 kilometers per second, time would actually slow down for you relative to someone who remains on Earth. This phenomenon, known as time dilation, means that while you might experience a few hours on your journey, years could pass for someone observing you from a stationary position. This effect has been confirmed through various experiments, including those involving atomic clocks flown in airplanes, which showed that the clocks experienced less passage of time compared to those left on the ground, illustrating how velocity alters the perception of time. Additionally, gravitational time dilation comes into play, where time moves slower in stronger gravitational fields. For example, if you were on the surface of a massive planet, time would pass more slowly for you compared to someone far away from any significant gravitational influence, such as in deep space. This is not just a theoretical concept. It has practical applications, such as the Global Positioning System, or GPS, satellites, which must account for both types of time dilation to provide accurate positioning information. When it comes to distance, frames of reference also change how we perceive the space between objects. In the context of relativity, two observers moving relative to each other will measure different distances for the same object. This effect is known as length contraction, where an object moving at a significant fraction of the speed of light will appear shorter in the direction of motion from the perspective of a stationary observer. This can be quite mind-boggling, as it challenges our everyday understanding of how distance is measured and perceived. Moreover, the concept of simultaneity is also affected by frames of reference. Two events that appear to happen at the same time for one observer may not appear simultaneous for another observer moving relative to the first. This leads to time dilation, a fascinating concept rooted in Einstein's theory of relativity, has intriguing theoretical implications for the idea of time travel. Essentially, Time dilation occurs when an object moves at a significant fraction of the speed of light, or when it is situated in a strong gravitational field, causing time to pass at different rates for observer in different frames of reference. This means, for example, that if you were to travel in a spacecraft at near light speed, time would pass more slowly for you compared to someone remaining on Earth, creating a kind of time travel into the future. This effect has been confirmed through experiments, such as those involving atomic clocks flown in airplanes, which show that the clocks that travel at high speeds measure less elapsed time than those that remain stationary. The implications of time dilation stretch far beyond just theoretical discussions. They raise the tantalizing possibility of human time travel, albeit primarily into the future. If we could harness technology to reach speeds close to that of light, a person embarking on such a journey could return to find that many years have passed on Earth, while they themselves have aged only a few months or years. This concept is often depicted in science fiction, but it is grounded in real physics, making it a captivating topic for both enthusiasts and scientists alike. However, the idea of traveling back in time is significantly more complex and introduces additional theoretical challenges. While time dilation allows for forward travel into the future, traveling backward in time would require conditions that are not currently understood within the framework of modern physics. Some theories suggest the existence of wormholes, hypothetical passages through space-time that could create shortcuts between different points in time and space. These wormholes, if they exist, could potentially allow for backward time travel, but their stability and traversability remain subjects of intense speculation and debate among physicists. Moreover, the concept of causality, which dictates that cause precedes effect, raises questions about the implications of changing past events. This leads to paradoxes, such as the well-known grandfather paradox, where a time traveler might prevent their own existence by altering events in the past. Such paradoxes add layers of complexity to the study of time travel, suggesting that if time travel were possible, it might be governed by rules that we have yet. Additionally, some physicists propose that time itself may not be as linear as we perceive it. Instead, it might be more akin to an intricate tapestry, where different timelines could coexist simultaneously. This advancements in propulsion technology could significantly influence time dilation effects in space travel, as they might enable spacecraft to reach a substantial fraction of the speed of light, which is where time dilation becomes pronounced, according to the theory of relativity proposed by Albert Einstein. As we know, time dilation occurs when an object approaches the speed of light, causing time to pass differently for that object compared to an observer at rest. Therefore, if we develop propulsion systems capable of achieving these high velocities, such as those that might utilize concepts like ion propulsion, nuclear thermal propulsion, or even theoretical constructs like warp drives, we could see notable differences in how astronauts traveling at these extreme speeds. For instance, If a spacecraft were to travel at 90% the speed of light, even a journey that takes a few years from the perspective of the travelers could equate to decades or centuries passing on Earth, which is a fascinating implication for deep space exploration and human longevity in space. Moreover, advancements in propulsion technology, such as the potential implementation of antimatter engines or solar sails, could not only shorten travel times to distant planets or stars, but also alter the conditions under which time dilation effects are experienced. As the efficiency and power of these technologies improve, scientists could explore the effects of prolonged exposure to relativistic speeds on biological systems, potentially leading to new understandings of human physiology in space. Additionally, innovative propulsion methods may facilitate missions to the outer solar system or beyond, where time dilation might play an even more crucial role in mission planning and the psychological well-being of astronauts, as they grapple with the reality of time passing different themselves and their loved ones back on Earth. Furthermore, advancements in propulsion technology could lead to scenarios where time travel, or at least significant time manipulation, becomes a topic of exploration. If we could achieve and sustain speeds that bring us closer to the speed of light, we might not only witness time dilation effects in action, but also raise ethical and philosophical questions about the implications of such travel. As we enhance our understanding of physics and push the boundaries of technology, the prospect of experiencing time differently during space travel becomes an intriguing frontier, prompting questions about our place in the universe and the nature of time itself. All this indicates that the intersection of propulsion technology and relativity could open up new horizons for humanity, making the exploration of the cosmos not only a physical journey, but a profound temporal experience as well. Scientists face numerous challenges when it comes to testing theories of time dilation in space, particularly because time dilation is a concept arising from Einstein's theory of relativity, which suggests that time moves at different rates depending on the speed of an object and its position in a gravitational field. One significant challenge is the need for precision in measurements, as time dilation effects are often minuscule, requiring incredibly accurate instruments to detect any shifts. For instance, atomic clocks, which are critical for these experiments, must maintain extreme levels of accuracy, often within billionths of a second, to observe the subtle differences predicted by relativistic physics. Another hurdle is the environment of space itself, which can be unpredictable and hostile. Space missions, such as those involving satellites or spacecraft, endure various factors, including cosmic radiation, temperature fluctuations, and even the gravitational influences of nearby celestial bodies. These conditions can affect the performance of equipment and the reliability of the data collected, complicating the interpretation of results. Moreover, deploying experiments in space demands significant resources, both in terms of funding and time, making it challenging to conduct repeated tests or long-term studies that could provide clearer insights into the effects of time dilation. Furthermore, the vast distances involved in space missions present logistical challenges. For example, testing time dilation effects with spacecraft traveling at high speeds, such as those approaching a significant fraction of the speed of light, requires journeys that can take years, if not decades, to complete. This means that results may take a long time to return, and by the time the data is analyzed, advancements in technology may have changed the landscape of scientific inquiry. Additionally, when scientists attempt to study time dilation using satellites in orbit, they must account for the differences in gravitational potential between the satellites and the surface of the Earth, which adds another layer of complexity to their experiments. Moreover, there is the challenge of public understanding and acceptance of these concepts. Time dilation can seem counterintuitive, leading to misconceptions that can hinder effective communication about the science involved. When scientists conduct outreach or educational programs, they need to convey the principles of relativity in a way that is accessible to the general public while still being scientifically accurate, which can be a delicate balancing act. Lastly, there is the issue of collaboration across disciplines and countries, as testing time dilation often requires a blend of expertise in physics, engineering, and technology, along with international cooperation for missions that may involve multiple nations. Coordinating efforts, sharing data, and agreeing on methodologies can be time dilation, a fascinating concept arising from Einstein's theory of relativity. Significantly influences how time is experienced in different gravitational fields, and this can have intriguing effects on living organisms in space. In essence, time dilation means that time can pass at different rates depending on your speed or your proximity to a massive object. For example, astronauts aboard the International Space Station, traveling at about 17,500 miles per hour, experience time slightly slower than people on Earth. This effect, while minuscule on the scale of a few hours or days, can accumulate over longer periods, resulting in measurable differences over extended missions. When considering biological processes, such as metabolism, cell division, and even aging, time dilation could theoretically lead to differences in how these processes unfold in space compared to Earth. However, for living organisms, the effects may not be as straightforward as simply experiencing time differently. Research indicates that the human body, along with other life forms, operates within a specific range of time and environmental conditions, and any significant alteration, such as the microgravity of space, can lead to changes in biological functions. For instance, studies have shown that astronauts exhibit muscle atrophy and bone density loss during prolonged stays in microgravity as their bodies adapt to the lack of gravitational stress. Moreover, time dilation might influence how biological rhythms like sleep cycles are regulated. The circadian rhythm, which governs sleep, wake cycles, and other physiological processes, relies heavily on the regular cycle of Astronauts often struggle with sleep issues due to the absence of natural light cues. And this disruption can affect hormone production and other bodily functions, irrespective of time dilation effects. Additionally, the perception of time itself can alter an astronaut's psychological state. In an environment where day and night do not exist as they do on Earth, the feeling of time can stretch or compress, potentially impacting mental health and well-being during space missions, especially those that last for months or years. While time dilation presents a theoretical framework for understanding how time might differ for astronauts in space, the real-world biological implications are complex and intertwined with other factors such as microgravity, radiation exposure, and psychological stressors. As researchers continue to study the effects of long-duration spaceflight, including missions to Mars or beyond, understanding how these various elements interact will be crucial for ensuring the health and safety of astronauts in the challenging environment of space. Time dilation, a fascinating consequence of Einstein's theory of relativity, occurs when an object moves at a significant fraction of the speed of light or is in a strong gravitational field, resulting in the passage of time being experienced differently for observers in varying frames of reference. For astronauts spending extended periods in space, particularly in environments where they experience microgravity and other stresses, the psychological impacts of time dilation can be intriguing and complex. Astronauts, who may travel on missions that last several months or even longer, can find themselves grappling with feelings of disconnection from Earth, as the way time is perceived can vary drastically from those living on the planet's surface. This disconnection can lead to a sense of isolation, as friends and family back home age in what feels like a different timeline. As astronauts are immersed in their daily routines aboard the spacecraft, the normal rhythms of life on Earth, including seasons changing, holidays, and significant life events, can start to blur, creating a psychological gap that may be challenging to navigate. The feeling of being out of sync with the world can contribute to feelings of loneliness or anxiety, as they may worry about their loved ones and how their absence is affecting relationships. Moreover, the mental strain of being in a confined space, combined with the effects of microgravity on the body, can exacerbate these feelings. Astronauts often report experiencing mood swings, irritability, and difficulties concentrating, which can be attributed to a mix of physical and psychological factors. The body's response to living in a weightless environment, including changes in fluid distribution and muscle atrophy, can affect physical well-being, which in turn impacts mental health. Additionally, the perception of time itself can alter astronauts' routines and their sense of time management. When days blend into one another, it can be difficult to maintain a structured schedule. This might lead to an increase in stress levels, as astronauts may find it hard to distinguish between work and leisure, leading to potential burnout. In extreme cases, some astronauts have reported feelings of existential dread, as the vastness of space and the isolation can prompt deep reflections on life and purpose. Mitigate these psychological impacts. Space agencies like NASA have implemented various psychological support systems, including regular communication with mental health professionals, scheduled leisure activities, and opportunities for social interaction among crew members. These strategies aim to help astronauts maintain a sense of normalcy and connection to Earth, balancing the scientific and personal aspects of their missions. The concept of time dilation is a fascinating aspect of the theory of general relativity, which was developed by Albert Einstein in the early 20th century. To understand this relationship, we first need to grasp what general relativity is all about. Essentially, general relativity describes how gravity is not just a force, as previously thought, but rather a curvature of space-time caused by mass. In simpler terms, massive objects like planets and stars bend the fabric of space-time around them, and this curvature affects the motion of other objects and even the passage of time itself. Now, time dilation comes into play in two key scenarios, one involving speed and the other involving gravity. When it comes to speed, according to Einstein's theory, the faster an object moves through space, the slower it moves through time, relative to an observer who is not moving. This means that if you were to travel at a significant fraction of the speed of light, time would pass more slowly for you than for someone who remains stationary on Earth. This phenomenon has been confirmed through various experiments, such as those involving atomic clocks on airplanes, which have shown that clocks on fast, moving aircraft tick slightly slower than those on the ground, consistent with Einstein's predictions. On the other hand, gravity also plays a crucial role in time dilation. General relativity posits that the stronger the gravitational field, the slower time passes. For instance, if you were to stand at the surface of a massive planet, you would experience time at a different rate compared to someone far away from that planet's gravitational influence. This has been experimentally verified using precise atomic clocks placed at different altitudes. Clocks closer to the Earth, where gravity is stronger, tick slightly slower than those positioned higher up, where the gravitational pull is weaker. The implications of time dilation are profound, not just for theoretical physics, but also for practical applications, such as the global positioning system, or GPEEPs. Satellites in orbit experience both forms of time dilation. They move quickly relative to observers on Earth, and they are also farther from the Earth's gravitational field. Engineers must account for these effects, adjusting the time signals sent by satellites to ensure that GPS remains accurate, which illustrates how intertwined time and gravity are in our everyday technology. Moreover, when we consider extreme environments, such as those near black holes, the effects of time dilation become even more dramatic. As one approaches the event horizon of a black hole, time appears to slow down dramatically from the time dilation is a fascinating phenomenon predicted by Albert Einstein's theory of relativity, and it describes how time can pass at different rates depending on an object's speed and gravitational field. When we consider high-altitude flights, such as those taken by commercial airliners, we start to see how time behaves differently compared to observations made on the ground. At high altitudes, airplanes are not only traveling at considerable speeds, but they are also further away from the Earth's gravitational pull, which is stronger at lower altitudes. This combination of speed and reduced gravitational influence leads to measurable time dilation effects. In practical terms, during a flight, the clocks on the airplane will run slightly slower than those on the ground, due to both the velocity of the airplane, since it's moving at a significant fraction of the speed of light, and the fact that it's at a higher altitude. This means that passengers on a flight might experience a tiny bit less passage of time compared to people who are still on the ground, even though this difference is extremely small and often imperceptible in everyday life. However, scientists have actually measured these effects using precise atomic clocks, which have shown that, indeed, time does pass more slowly for the clocks on airplanes than for those on the ground. For example, experiments involving atomic clocks placed on planes and compared to identical clocks on the ground have shown that after a flight, the airborne clock registers a time that is slightly behind that of its ground counterpart. This effect is more pronounced in longer flights, especially those that occur at higher altitudes and greater speeds, such as transcontinental or intercontinental flights. The actual difference can be on the order of microseconds, which is a very small amount, but it is a real effect that has been confirmed by various experiments and observations. As we delve deeper into the implications of time dilation in aviation, it's important to note that this phenomenon is not just a theoretical curiosity, but it has practical ramifications as well. For instance, the Global Positioning System, GPS, which is crucial for navigation, relies on a network of satellites in orbit around the Earth. These satellites experience time differently than clocks on the ground, due to both their speed and their distance from the Earth's gravitation. Engineers account for time dilation effects when calculating the timing signals sent from these satellites, ensuring that GPS remains accurate for users on the ground. In conclusion, time dilation effects in high-altitude flights illustrate the intriguing ways in which our understanding of time and space can change based on velocity muons, which are elementary particles similar to electrons, but with a much greater mass, that demonstrate time dilation, a key concept in Einstein's theory of relativity. The significance of muons in this context arises from their unique properties and their relatively short lifespan, which is about 2.2 microseconds when at rest. When muons are created high in the Earth's atmosphere, they are produced as a result of cosmic ray interactions with atomic nuclei. These muons travel towards the surface of the Earth at speeds close to that of light. and due to their high velocity, the effects of time dilation become quite pronounced. According to the principles of special relativity, time appears to pass more slowly for objects moving at speeds close to the speed of light compared to those at rest. When scientists measure the number of muons that reach the Earth's surface, they find that a significant number survive their journey, far exceeding what would be expected if they did not experience time dilation. From the perspective of an observer on Earth, these muons are moving so quickly that their internal clocks run slower compared to those of stationary observers. This phenomenon can be observed in experiments where detectors placed on the ground capture muons that should have decayed long before reaching the surface based on their rest frame lifespan. Instead, the muons are detected in numbers that can only be explained by the time dilation effect, which allows them to exist longer from the perspective of the stationary observer as time for the fast-moving muons slows down. These findings have been confirmed through various experiments, reinforcing the predictions made by relativity and providing concrete evidence that supports the theory. Furthermore, the implications of muons in demonstrating time dilation extend beyond just academic curiosity. They have practical applications in fields like particle physics, and even in the technology behind GPS satellites. Since these satellites move at high velocities relative to an observer on Earth, the effects of time dilation must be accounted for to ensure accurate positioning. Therefore, muons serve as an essential bridge between theoretical physics and real-world applications, highlighting the profound relationships between time, speed, and the fundamental nature of particles in our universe. This interplay of high-energy physics and relativistic effects continues to inspire both scientists and enthusiasts alike, reminding us of the complex yet beautiful tapestry that is woven throughout the cosmos. The speed of a spacecraft plays a crucial role in determining how long it takes to reach its destination. And from the perspective of Earth, this is particularly fascinating. When a spacecraft is launched, its velocity is influenced by several factors, including the propulsion system, the gravitational forces of celestial bodies, and the design of the mission itself. For instance, consider a spacecraft traveling to Mars. If it travels at a high speed, it can cover the distance between Earth and Mars in a shorter time, which is often the goal of mission planners. The average distance to Mars is about 225 million kilometers, but depending on the positions of the planets, this distance can vary significantly. If a spacecraft travels at about 100,000 kilometers per hour, it could make the journey in roughly 225 days. But if it can achieve higher speeds, such as 250,000 kilometers per hour, the trip could be reduced to around 90 days, demonstrating how speed impacts travel time. Moreover, the speed also affects fuel consumption and mission design. Faster speeds require more powerful engines and consequently more fuel, which adds weight to the spacecraft and can complicate the engineering design. This is why many missions use gravity assists, where a spacecraft uses the gravitational pull of planets to increase its speed without using extra fuel. For example, the Voyager spacecraft utilized gravity assists from Jupiter and Saturn to gain the velocity needed to travel into the outer solar system, significantly shortening the duration of their journey. Additionally, the physics of space travel involves a concept known as the Hohmann transfer orbit, which describes the most efficient route between two orbits, such as from Earth to Mars. This method takes advantage of the positions of the planets and the spacecraft's speed to minimize energy use while maximizing travel efficiency. When a spacecraft is launched, it must reach a specific speed to break free from Earth's gravity, known as escape velocity, which is about 11.2 kilometers per second. This speed is essential for any spacecraft intending to leave Earth and travel to other celestial bodies. It's also interesting to note that the speed of light, which is approximately 300,000 kilometers per second, serves as a cosmic speed limit. This means that no information or matter can travel faster than light. Consequently, when we observe distant galaxies or stars, we are looking back in time, due to the time it takes for that light to reach us. In contrast, spacecraft traveling at speeds much slower than light can take years, or even decades. When we think about the fascinating concept of time dilation, it's essential to realize that this phenomenon, predicted by Albert Einstein's theory of relativity, suggests that time can move at different rates under varying conditions, especially when it comes to speed and gravity. Space missions designed to test the limits of time dilation not only excite the imagination, but also push the boundaries of our understanding of physics and the universe itself. One of the most talked about missions is the potential for a crewed mission to Mars, which, due to its distance from Earth, would involve significant travel time. And if the spacecraft were to travel at a substantial fraction of the speed of light, of time, compared to people remaining on Earth. This difference in the passage of time is a real-life test of time dilation, as astronauts could return to find that more time has passed on Earth than for them. Another proposed mission that captures attention is the idea of sending spacecraft to study the effects of time dilation near a black hole, particularly around the event horizon, where gravity is at its most intense. Theoretical proposals suggest a mission that involves sending probes into what is known as the gravitational well of a black hole, where time would pass much more slowly for the probes compared to observers far away. While such a mission is fraught with technical challenges and ethical considerations about the safety of the probes, it would provide invaluable data about the extreme conditions of space-time. Additionally, the Laser Interferometer Space Antenna, or LISA, is a proposed mission that aims to detect gravitational waves. As part of this mission, scientists predict they could observe time dilation effects due to the massive celestial bodies that create these waves. By measuring the incredibly subtle changes in distance between spacecraft as they move through space-time, Lisa could help confirm predictions made by general relativity and deepen our understanding of how gravity influences the passage of time. Moreover, there are concepts surrounding near-light-speed travel, such as the Alcubierre warp drive, which theorizes a method of space travel that could allow a spacecraft to move faster than light without violating the laws of physics. If such a technology were developed and implemented, missions utilizing this method could lead to extraordinary experiments in time dilation, as astronauts would age more slowly during their journeys compared to those who remain stationary. Finally, experimental satellites and missions, such as the Gravity Probe A, have already provided evidence of time dilation effects due to gravitational differences. As they time dilation, a concept rooted in Einstein's theory of relativity, in fascinating ways. In simple terms, time dilation refers to the phenomenon where time passes at different rates for observers in different frames of reference, especially when one is moving at a significant fraction of the speed of light, or is in a strong gravitational. Imagine a scenario where a twin travels on a spaceship at near light speed, while the other twin remains on Earth. The traveling twin will age more slowly than the twin who stayed home, due to the effects of time dilation. This scenario, often referred to as the twin paradox, illustrates how our intuitive understanding of time, which suggests that it flows uniformly for everyone, is not entirely accurate. When we think about cause and effect, we usually assume that events unfold in a linear fashion, where a cause precedes its effect in a clear and consistent order. However, time dilation introduces a twist to this perspective, especially when you consider high-speed travel or environments near massive objects like black holes. In these situations, observers may not agree on the order of events. For example, if two events happen simultaneously for one observer, they may occur at different times for another observer moving at a different speed. This leads to a situation where the traditional cause and effect relationship becomes blurred, as the same event can be perceived differently depending on the observer's frame of reference. Moreover, time dilation is not just a theoretical concept. It has practical implications in our everyday lives, such as in the Global Positioning System, or GEBE. The satellites orbiting the Earth experience time slightly differently than people on the ground due to their speed and the weaker gravitational pull they experience compared to those on the surface. Without accounting for these time differences, GP's calculations would quickly become inaccurate, demonstrating that time dilation is not merely an abstract idea, but a reality that affects technology and navigation on Earth. As we delve deeper into the implications of time dilation, we encounter the idea of simultaneity, which is closely linked to the concept of causality. In classical physics, simultaneity is absolute. However, in the relativistic framework, events that are simultaneous in one frame may not be simultaneous. This leads to intriguing paradoxes, where one observer sees an event as a cause, while another sees it as an effect, challenging the very foundations of how we understand interactions in the universe. Furthermore, when we explore the nature of black time dilation, a phenomenon predicted by Einstein's theory of relativity has fascinating implications for the potential colonization of exoplanets, which are planets located outside our solar system. As humans consider the possibility of traveling to these distant worlds, it's important to understand how time dilation could affect both the journey and life on those planets. When a spacecraft travels at a significant fraction of the speed of light, time for the travelers aboard the ship would pass more slowly compared to people remaining on Earth. This means that if a group of astronauts were to embark on mission to an exoplanet and they traveled at near light speed, they might age only a few years during their journey, while decades or even centuries could pass on Earth. This disparity could lead to complex social and psychological challenges, particularly for the travelers who might find themselves returning to a vastly changed Earth with friends and family, either much older or possibly even deceased. Moreover, if we consider the implications of establishing a permanent human presence on an exoplanet, time dilation would also play a crucial role in how we perceive and manage time on that new world. Depending on the distance from Earth and the speed of travel, the time it takes to communicate back home could be significantly delayed, creating a disconnect in real-time communication. For instance, if a colony is established on a planet orbiting a star several light-years away, messages sent between Earth and the colony could take years to arrive, which could hinder decision-making and coordination between the two locations. This might also affect the psychological well-being of colonists, as they could feel isolated from Earth, leading to a unique set of challenges for maintaining social cohesion and mental health. In addition, the concept of time itself could be influenced by the gravitational fields of different celestial bodies. As time runs slower in stronger gravitational fields, according to general relativity, this means that if colonization efforts are focused on planets with significantly different gravity compared to Earth, the experience of time could vary for the inhabitants, further complicating the relationship between the colonists and their home planet. Furthermore, these time dilation effects could impact the planning of long-term missions and the sustainability of life on exoplanets. As scientists and engineers design spacecraft and habitats for these journeys, they'll need to take into account not just the physical challenges of travel and living in different environments, but also the psychological and temporal factors that could influence the success of colonization efforts. Overall, as we scientists simulate time dilation effects in laboratory settings using a combination of advanced technology and principles of physics, primarily derived from Albert Einstein's theory of relativity, time dilation which suggests that time moves slower for objects moving at high speeds compared to those at rest, can be observed in various scenarios, such as when particles move close to the speed of light or in strong gravitational fields. To explore these fascinating effects in a controlled environment, researchers often utilize particle accelerators, which are large machines designed to accelerate charged particles, like electrons, to speeds that approach the speed of light. In these accelerators, scientists can create conditions that mimic the high-velocity environments of space, allowing them to observe how time dilation affects the particles. For instance, when particles are accelerated to such high speeds, their decay rates change as predicted by time dilation, which means that they appear to exist longer than they would at rest. This effect can be measured with precision, providing researchers with clear evidence supporting Einstein's theories. Furthermore, researchers also explore gravitational time dilation, which occurs in the presence of strong gravitational fields. To simulate this in the lab, scientists often use highly accurate atomic clocks, which can measure time with incredible precision. They place these clocks at different heights, as gravity weakens with distance from the Earth's surface. The clocks at higher altitudes will tick slightly faster than those at lower elevations, demonstrating the effects of gravitational time dilation in a measurable way. Additionally, some experiments involve using lasers and interferometers to measure changes in time and space as they relate to high speeds and gravitational influences. These experiments help to reinforce our understanding of how time behaves differently under various conditions, and they provide valuable insights into the nature of the universe. Moreover, researchers also use technology such as very high-speed cameras, which can capture rapid events, enabling them to study the effects of time dilation in real time. When analyzing the results, scientists compare the observations to the predictions made by the equations of special and general relativity, which helps to further validate the theory. As our understanding of time and space evolves, these simulations not only enhance our knowledge of fundamental physics, but also have practical implications in fields like GPS technology, where time dilation must be accounted for to ensure accuracy and location tracking. This ongoing research not only deepens our comprehension of time itself, but it also opens doors to new technologies and applications that can benefit society, reflecting the profound connection between theory and practical use in the realm of science. The concept of time dilation, which arises from Einstein's theory of relativity, presents intriguing cultural and philosophical questions that challenge our understanding of time, existence, and reality itself. When we think about time, we often view it as a constant, a steady flow that ticks away uniformly for everyone. But time dilation suggests that this is not the case. Imagine an astronaut traveling at a significant fraction of the speed of light, experiencing time at a different rate than someone on Earth. This creates a scenario where two individuals can experience the passage of time differently, leading to profound questions about the nature of if time can stretch and bend based on speed and gravity, what does that mean for our perceptions of life and death? For instance, if one person ages more slowly due to time dilation, how do we measure the value of their experiences compared to someone who has... This leads to philosophical inquiries about the meaning of life, as the perceived lifespan and experiences can vary dramatically depending on one's position in the universe. Furthermore, time dilation raises questions about memory and identity. If our memories are tied to our experiences over time, how do people who experience time differently relate to their past? Is identity anchored in the linear progression of time, or can it be understood in a more fluid way? This could influence cultural narratives, where stories and histories might be perceived differently by those who have experienced time at varying rates. Additionally, it can spark discussions about the nature of consciousness itself, as we consider whether consciousness is a universal experience or one that is relative to the time experienced by the individual. In literature and art, time dilation can inspire new interpretations of storytelling, where narratives might intertwine characters who experience time differently, challenging audiences to rethink how they perceive time and its impact on relationships. For instance, science fiction often explores these themes, presenting scenarios where characters confront the emotional and philosophical implications of time travel or interstellar journeys that lead to significant time disparities. Moreover, there are cultural implications in how societies might adapt to the understanding of time dilation. If we can send explorers to distant planets at speeds that cause them to return home years later, how would that alter our concepts of family, community, and belonging? Would relationships be strained by the different timelines, or would they evolve to accommodate this new reality? The implications of time dilation also touch on ethics as we consider questions about responsibility. If someone has experienced time differently, does that affect their moral decisions? Are they held as we delve into the fascinating concept of time dilation, particularly in the realm of space travel? It's important to understand that time dilation occurs due to the effects of Einstein's theory of relativity, which describes how time can pass at different rates depending on an object's speed and gravitational field. For future space travelers, technologies that could potentially mitigate the effects of time dilation are both intriguing and complex. One such approach could involve advancements in propulsion systems, specifically those that allow spacecraft to achieve a significant fraction of the speed of light. If we could harness technologies like nuclear fusion or antimatter propulsion, which are still largely theoretical, we might be able to reduce the time dilation experienced by astronauts traveling vast distances by maintaining a higher velocity for shorter periods. The time experienced by the crew could align more closely with Earth's time, creating a more manageable experience during long missions. Another promising avenue lies in the development of artificial gravitational fields. By simulating gravity on a spacecraft, we not only provide a more comfortable environment for the crew, but also potentially influence the effects of time dilation. Scientists are exploring the use of rotating spacecraft to create centrifugal force, which mimics gravity, and this could help counter some of the physiological impacts of extended space travel. Furthermore, researchers are investigating advanced materials and technologies that can withstand extreme conditions in space, which could support the construction of habitats that are more resilient and capable of sustaining life for longer periods, thereby allowing for longer missions without the severe impacts of time dilation. Quantum technologies may also play a vital role in our understanding and potential mitigation of time dilation. Quantum entanglement, for instance, allows information to be transmitted instantaneously across distances. While this does not directly mitigate time dilation, it could pave the way for innovations in communication systems that keep astronauts connected to Earth, allowing for synchronized experiences and minimizing the psychological effects of being away for extended periods. Moreover, as we look towards the future, the integration of artificial intelligence and machine learning could assist in optimizing spacecraft operations, analyzing data in real time, and making adjustments that could, in theory, help manage the effects of time dilation on crew members. By predicting and simulating various scenarios, these technologies might allow us to devise strategies that keep the passage of time more consistent for travelers. Furthermore, understanding the biological effects of time dilation on humans is crucial. Research into human physiology in microgravity environments is ongoing, and by developing better life support systems, we can ensure that astronauts remain healthy and functional, effectively reducing the subjective experience of time dilation, a fascinating aspect of Einstein's theory of relativity. Presents intriguing implications for our understanding of the universe's lifespan. Essentially, time dilation refers to the phenomenon where time passes at different rates depending on relative speeds and gravitational fields. For instance, when an object moves at a significant fraction of the speed of light, or when it is in a strong gravitational field, time can slow down for that object relative to an observer in a different frame of reference. This has incredible implications for how we perceive the age and evolution of the universe. If we consider the vast distances of space and the speeds at which galaxies move, time dilation could mean that what we observe from Earth may not accurately reflect the true passage of time in other parts of the universe. For example, if a spacecraft were to travel close to the speed of light, the crew aboard would experience time much more slowly compared to people on Earth. This concept leads to the idea that while we might think the universe has existed for around 13.8 billion years, the experience of time could be dramatically different for entities moving at relativistic speeds. Moreover, time dilation could also affect our observations of cosmic events, such as supernovae or the formation of stars and galaxies. If time behaves differently across various regions of space, we might misinterpret the timing and life cycle of these cosmic phenomena, potentially altering our understanding of how long the universe has been evolving or how long it might continue to evolve in the future. Additionally, the implications of time dilation extend to the study of black holes, where the gravitational pull is so intense that time effectively comes to a standstill at the event horizon. This phenomenon raises profound questions about the ultimate fate of matter and energy in the universe, as well as the potential for time travel or parallel universes. If we could find ways to understand and measure these effects accurately, it could lead to a revised timeline of cosmic history, as well as new theories about the universe's eventual demise. Furthermore, as we explore concepts such as dark energy, which seems to be accelerating the expansion of the universe, the interplay of time, dilation with these forces, could reshape our understanding of cosmic dynamics. If time is not a constant and varies across the universe, it could mean that the expansion of the universe is not uniform, leading to new interpretations of the data we collect from distant galaxies. Understanding time dilation could also deepen our grasp of fundamental physics, as it challenges our conventional notions of time and space. As scientists continue